So, good morning, everyone, to the session on raw materials, critical raw materials. It's good to see that everyone is enjoying this opportunity to have face-to-face exchanges, and I propose to slowly settle down and to get started to this session. So my name is Klaus Peters, for the ones who don't know me, and I have the pleasure to moderate for you today's session on critical raw materials. And materials, we just have, I think, all experienced the material manifesto in the plenary session a few minutes ago, and materials are all around us. So they are, I like to say, as a secondary skin to us. And this we enjoy almost unconsciously, which is not bad at all. However, sometimes, of course, the skin needs some attention, and in particular, if something goes wrong. So therefore, we have a couple of initiatives like the Material Manifesto and also the definition by the Commission on some materials which needs special attention because they are critical raw materials. And I'm very delighted to have 4 experts in the field who will illustrate the role, the importance, and appropriate measures to tackle these critical raw materials in a good way, to master the challenges we suffer together from the disturbances of the value chain, as well as with the Ukraine war situation, while we are still, of course, fully committed to our ambitions from the Green Deal, and also to increase the level of sovereignty for Europe. And having said this, I'd now like to introduce to you the 4 speakers, and I'd like to do this in the sequence of their interventions. So the first speaker will be Fabrice from Umicore. He's their director in the Brussels-based governmental affairs section, and he's very active in the field of hydrogen, batteries, recycling for renewable energy and industry as such. And I know him in person very well from his time as the managing director of Emery. So thank you very much, Fabrice, for being with us. And the second speaker will be Katharina. She's the director of the Alba synchrotron. So she will add, next to the industry perspective, an academic perspective to the field of critical raw materials. We are very much looking forward to your views in this regard. And staying in the academic field, I'm also very happy to welcome Professor Vaiko from the Tallinn University. And we are also very happy to have you with us. He will provide to us a couple of examples from his perspective, outlining the important role of critical raw materials in the various fields of our experience. And last but not least, we will have a very deep dive, so to speak. Oh, sorry for that. That's a good reminder for you to do this as well. And before we go to the deep dive presented to us by Frederick, which is in the field of magnets, which relies very tremendously on a subset of the critical raw materials. And hopefully we will have then a good time to engage with all of you in a Q&A session. So please do not hesitate to make your comments and raise your questions in Slido. If you don't like these digital tools, you can also consider to raise your question directly, but of course it has some limitations for the recording in this regard. So, having said this, now it's time for you, Fabrice, to take the floor. Thank you very much again for being with us, and I leave the stage to you.
I put my chronometer. Let's page down over this.
To the right.
Okay.
Try it. You can just try if it's working. Oh, perfect.
No, it works. Okay, so thank you so much, Klaus, for the introduction and the invitation. I'm going to fight with the microphone. So what I wanted to give you today is a broad overview of the case of circular economy and how it can help, of course, to deal with this very timely issue that we have with access to critical raw materials. But I would like to look at circular economy from the point of view of the challenges that we still have to solve, because this is not a magic bullet, and also propose some solutions, key actions that, as the industry, we see the need to develop in the future, not alone, but with the help of the policymakers and with the help of the research community. First, I have to do a little bit of promotion and marketing about Umicore. So we are a 11,000 people company. We are Belgian by DNA, I would say, but we are global. And we focus on three main activities. The first one is emission control. We are one of the three global leaders in emission control catalysts. So what you have at the end of your car, if you are still driving non-electric, is maybe containing our products. But it's also for heavy-duty vehicles, which are more the trucks and the vans and the caravans, whatever you call it. The second big pillar, and actually is, I guess, going to become a major pillar in the future, as we all know it, it's the battery materials, where we are also one of the key providers of the cathode materials. So this is what is at the positive part of the lithium-ion battery. And we also support the hydrogen economy with fuel cell catalysts and electrolyzer catalysts for the PEM technology. And then we close the loop. Even before it was called circular economy, we were doing it. And we are the biggest recycler of complex waste streams that contain precious metals like gold, platinum, rhodium, ruthenium, you name it. Actually, what you can see on the bottom of the slides, if it's not too small, is the list of the main metals that we recover. And of course, you can see these are quite expensive metals, not the typical big volume metals that you see out there, but really the ones that are either critical or strategic. And we do this at an industrial scale, so we don't talk only about recycling, we also do it. And what you can see on the picture here on the left, this is our, I would say, one of the biggest recycling plants in the world for metals. It's based in Hoboken in Belgium, next to Antwerp, conveniently located, of course, along the river for logistics, and actually very close to the population, which obliges us to behave in the best way when it comes to EHS standards. We recover more than 17 metals, and it's one process which is dimensioned in such a way that we can recover them and separate them. And we either treat production waste, but we also treat end-of-life fractions, so it can be catalysts from the automotive industry, from the chemical industry, printed circuit boards, electronic waste, industrial waste, and of course, we also now develop the battery recycling activity, which is a separate technical setup, still on the same site, where we are already ready to pilot it at the 7,000 ton scale. But when I said 7,000 ton, and if you look at here, one you can see on the left, it's actually 500,000 tons. So it gives you an idea of the future size as well of battery recycling in the world. It's going to be similar sizes. A little bit of policy background. This is a study that has been made by the European Commission a couple of years ago, where they have been looking at all the typical metals that are considered scarce and how they distribute over the main technologies that we need for the green and digital transition. And as you can see, without them, we will not be able to move on. And a point I want to make, which is more on the right of the slide, is that we are not good on raw materials, but we are not much better on the processed materials. So the point I want to make is that if you are able to source critical raw materials and you do not transform them into active advanced materials in Europe, actually you're not solving a problem. You are just solving half of the problem. So when we talk about materials, we should consider the raw, but also the advanced materials. So one solution is, of course, circular economy, which is about closing the loop, starting from the ore, then to the smelter, refiner, the non-ferrous metals, example here. Then we made active materials, which we also call technology materials in the field. Then you do application. They come to the end of life. You have to recover them, and then they can go back into the loop. So this is how it works. For your information, what you can see on the slide in the blue part, which is the top part, This is where Umico is involved, so we are no longer a mining company. We have had some heritage in the mining sector, but we are no longer a mining company. And what you can see on the bottom is actually the typical other actors of the value chain which also need to do their part. So there are a couple of challenges that I wanted simply to share with you today to paint the picture. The first challenge is that high resource efficiency and circular economy, they start when you develop a product and when you manufacture it. So don't wait until the product is coming to the end of life to do circular economy. Circular economy starts from the start. And the best example is when you develop advanced materials. It's a way to connect to the manifesto and to the roadmap of today. If you are able to diminish the amount of a metal that is contained in an application, you're actually already solving the problem. You don't have to wait until the end. Best example is the batteries of today, the lithium-ion batteries. They contain less and less cobalt. But of course, it's not easy. Huh? If you remove the cobalt, you potentially destabilize the chemistry. So you have to find material solutions in order to be able to cope with that. And that's about putting more nickel and putting more manganese. So that's one example. Another example from the hydrogen technologies, we are trying to reduce the amount of platinum that is contained in the fuel cell catalysts. Another example from a maybe less futuristic technology, which is emission control, which we still need for the moment. There as well, we are trying to reduce the amount of platinum that is on the catalyst. So starting from the development of materials is the way to go. Then you also have to make sure that when you design an application that contains your material, it is designed in such a way that it is be able to last some time, that is durable, that you can repair it, you don't have to discard it, and that you can recycle it, because people who develop applications, sometimes they may not have enough circular economy background in the way they design, and they make it difficult for recycler actually to recycle. So everybody has to work together there. Another point is also the production waste. If you can minimize the production waste by having processing technologies that may be digital enabled, you will be able to actually use less material. And in a period of time where the price of materials is going up, it's also in your best interest to not have big inventories of materials that you are wasting. And then another element that is also important to us is that next to that, it would be nice if you would be sourcing materials in a responsible way, which is a small bracket on the side, but that's also very important if we talk about circular economy. You cannot have a non-ethical circular economy, because then it's really not the way to go. Challenge number 2, this is about collection. If you are not collecting, you are not recycling. So collection is very important. And there, it's very important to maybe to act more on the policy side rather than technology side, but we need to have legislation in Europe that fix collection targets. Important also obligations from the producer side. Whenever you put something on the market, you are liable to make sure that your product is coming back to the recycling plant, for example. Another tool that is very important, it's more technology, it's traceability and track systems. So that next to a product, you have now a digital layer, and you know at which any amount, any time in the lifetime of a product, where the product is. Maybe you also can collect information about the state of health, how it is being used, and you could also add to that some elements of ethical sourcing, CO2 footprint in producing the material. So what you're going to see in the future next to the product is product passports, which are actually containing information. Just like you when you travel around, it gives you access to some territories, but it also enables the authorities to know where you are and gets you back in case there's a problem. So that's the same thing with this technology. What we also need to do is motivate collection, and there's some elements like of infrastructure, but we also need to make sure that the citizens do not collect 15 mobile phones in 5 drawers at home. I'm sure you all have mobile phones which could be collected and recycled, so we have to find a way to incentivize the people. Challenge number 3, it's quite obvious, but if you collected something, don't lose it. And what we mean by this is that you have to stop in Europe questionable exports and substandard treatment. I'm sure you have all seen pictures of kids in Africa doing some what we call garage recycling, where they are burning stuff, they're exposing themselves to very toxic chemicals. They recover, by the way, far less than you could recover with Western technology. So this is something we have to stop. So we have to find a way to enforce legislation to ban illegal and dubious exports. Of course, if these exports would be legal, because they can also be legal, then we have to make sure that they are treated in optimal conditions, similar to what we do in Europe. We cannot export to be treated in suboptimal conditions. This is not what European people should be doing. And then in case, for example, you have something that you want to export from Japan to Europe, which is both very developed economies, you need to find a way to fast track the flow of products to recycle over the globe. Today we have a regulation which is called Basel, which is making the life of most recyclers very complicated. Even in some countries where the legislation is regional, like in Belgium, you have to file a Basel notification to cross the language border, which is also an element that is quite stupid when you think of it. So we need to find a way, with technology maybe, to make the Basel regulation more friendly to the industry, and by that also more friendly to the planet. Challenge number 4, it's high quality recycling. So what do we mean by high quality recycling? We mean that whenever a product is arriving at the end of the lifetime, they come to a recycling company, we should make sure that we are using the best available technologies, both in terms of environmental footprint, in terms of operator safety, in terms of impact on the environment, in terms of course, also of recovered content. If you have two technologies, one is able to recover 95% and the other one 90%, we should find a way to always promote the best technologies to make sure we do not waste very important metal. And there, the establishment of traceable, auditable, and ambitious minimum processing standards is the best way to move away from low quality to high quality. There's an example of a policy which is now being developed. This is the battery regulation that is being revised by the European Commission, the Parliament, and the Council of Member States, where there's going to be very ambitious targets in terms of collecting, but also in terms of recovery by the recycling processes, and then also very important targets in terms of what we call recycled content. So the batteries of the future will have to prove that they are partly manufactured from metals that are not mined, but recycled. And that's the best way to promote this circularity. And I will finish with a very complicated piece of mathematics, which is that if it's actually a loop, there are a sequence of steps, and logically, the weakest part of the link is the one that is ruining all the efforts of the others. So we have to really make sure that we do not think in silos when we consider circularity. Everybody has to be involved to make sure that everybody is doing its own part. And this is an example based on current statistic when it comes to recovery of gold from waste electronics. Typically, collection is not really optimal, 50%. Pre-processing is at 70%. The guys who are doing recycling, they are doing a hell of a job. They recover 95%, but they can only recover 95% of what is coming to them. And when you do the mathematics, then you end up with only 33% of the gold which is actually recovered. That means that 2/3 of the gold is out there, lying around, not collected, not pre-processed the right way, and well recycled, but there's a limit to what we can do as a Umicore company or other company. So this is really a call for more interactions in the future between the different parts of the value chains, between industry, policymakers, and the research worlds, if we want to be able to reduce our dependency on other powers of the globe. I don't believe that we are going to be able to reduce it completely. We have to be realistic. The geology of Europe is not the best in the world, but there are things that we can do to make sure that we are in a better position to negotiate with these countries in the future. Thank you. Do you have to do something?
No. Thank you very much, Fabrice, for sharing your insights with us from the perspective of this big material company, showing that the circular economy can be a solution. And still we need to work together. It's not an easy exercise. It remains a series of challenges. Thank you very much for that. And you already pointed out that material substitution may be part of the solution. So let's listen to Katharina. I like to welcome her now on stage. What kind of opportunities can you bring to the table from the research perspective to identify meaningful, promising material substitutions? The floor is yours. Thank you very much.
Thank you very much, and it's a pleasure to be here today. And my intervention is meant to show you what these synchrotrons can do to help in what is being discussed during this day in this very, very interesting meeting. And I will start with, I am the director of the ALBA synchrotron, so I will start with few information about ALBA. ALBA is a research infrastructure, is a user facility, is a public institution. It is therefore funded by public funds, and is open to users which come from academy, but also from industry. And this is very important because our scientific community comes from both sides, and many times they work together and they develop together. At ALBA, we have three big parts of science: life science, chemistry and material science, electronic and magnetic structure of matter. And a synchrotron is an accelerator which accelerates electrons, which produce the synchrotron light, which are X-ray. And this is the instrument we offer to the community, X-ray, in a huge number of different techniques of understanding how the light interacts with the matter, and from there obtain the information on the property of the matters. And there is here is a list of different techniques which are available and will be available at ALBA. But synchrotrons are going now towards an evolution from the third generation to the fourth generation, which means that the change in the technology of the accelerator, we are providing and we will provide photon beams even more qualified to have even more properties for understanding the matter in imaging, spectroscopy, diffraction. This is something that ALBA has just started, but we have here a few kilometers from here the SRF synchrotron, which is already has already gone to the fourth generation. This means that this technology is in evolution. Now, having said that, for the synchrotrons, you have seen a long list of techniques that are available, and I want to show few examples on how the synchrotrons can help in the part of understanding the materials. And we have heard so many times, and also this morning and now from Fabrice, that one of the points is the circular economy, and of course the CO2, to treat the CO2 in order to have carbon neutral technologies. And I want to use an example, which is a plant, a test plant by ThyssenKrupp, where there is a long change of different activities, where you start from a CO2 emitting industry, and then you go down to a carbon neutral product. And this is thanks to the development of catalysts. Catalysts, there are few examples here that you can activate CO2 to methane with ruthenium nanoparticles and many others. And these are examples that can be done in the synchrotrons. We need electrocatalysis, heterogeneous and homogeneous catalysis. And this is something that you can deal in our synchrotrons. Why catalysts is, what are the challenge of development of catalysts? You need to have better energy efficiency, smaller raw material consumption, higher selectivity. And the challenge is that the catalysis happens at the level of the surface. You were mentioning before the skin, the surface between different materials. And it's not only to understand where the atoms are, but also how these active atom is interacting with the nearby atoms. So you really need instruments which go down to the size of the atom and to the understanding the chemical part of this process. And the tools in the synchrotrons for that, you can do experiment ex situ, operando experiment, high throughput, and you see here that we can go from the far infrared spectroscopy to the hard X-ray spectroscopy. We saw before the list of elements that Umikor was showing. Why is important? Because we can produce those photons which interact with the electrons of the atom that we want to understand, and we go down to the energy resolution of 10 to minus 4, so we understand which atoms are in all these different processes. We have then microscopy, we have powder diffraction, and synchrotrons are also teaming up with another instrument, which are the electron microscope, and this is happening everywhere, also in Europe, because this is a complementary technique. Let's go now to another example. The second example is we have heard how it's important to have raw materials and which are the alternatives, for example, to titanium. The titanium applications they mainly are for the aerospace industry, and in this moment Western countries have direct access only to 22% of the world resources. So developing materials which can substitute or have a low composition from titanium is very important, and we have to develop new alloys that can be with new capabilities of machining and increase the energy performance of the titanium-based product. Also here, which are the challenges? We have to understand a different scale imaging of the crystal phases, crystal orientation, elemental segregation, understanding the nanostructure for the different application and how to create this optimum nanostructure. Where the synchrotron radiation helps, because you can really determine the structure over multiple length scales. Here there are examples. You can do tomography at a large volume. You can go down to tomography with using nanodiffraction. You can check the single crack imaging in a dynamic way. So here in the synchrotrons, also here you can do microscopy with ex situ experiments, operando experiments, high throughput, and also in this case the high resolution TM for imaging at the larger dimension. And finally, as a last example of the many that I could have used is the carbon nanotube, which is a material which is increasingly becoming more important for different applications. For example, for reducing the weight and the amount of copper in aerospace, in turbines, or to produce new conductors with very good electrical capacities. And the challenge is that we need also here to create catalytic nanoparticles in the gas phase to make the optimization for the reaction condition, and to obtain this carbon nanotube with the appropriate length for their usage in the industry. Synchrotron radiation, we can use also here other techniques like the small angle scattering or wide angle scattering, and of course again spectroscopy, soft X-ray absorption and soft X-ray resonant scattering, plus the interaction with the electron microscope. And so there are these are few examples, but I want to show you. I started with ALBA, but it's not only ALBA, of course. In Europe, there are several synchrotrons, there are several free electron lasers, and what we did a few years ago was to create LEAPS. LEAPS stands for Liga of European Accelerator-Based Photon Source, and is in this moment the largest consortium of analytical facilities worldwide. This is a real strength of Europe to have such a different a large number of different facilities, and now we work together in the sense that we plan together technological development, we plan together to work with the European Commission in projects that are funded by the European Commission. Altogether, we offer more than 300 operating stations, which means that we are offering more than 1 million of hours of beam time to all the community. And again, I want to stress that the academic community is our main user, but the industrial community is more than welcome, and is we are aiming at increasing the part that the industry is using in our facilities. And these facilities are, most of them are national facilities, as ALBA is, so they are funded by each country, but they are open to the whole Europe. And I address those of you who are not in one of the countries which host a synchrotron, that you are also one of our users, and you are more than welcome to use that. Recently, we have prepared what we call ESAPS, European Strategy of Accelerator-Based Photon Sources, which is how we see LEAPs working in the future to better serve the society, better serve Europe, better serve the technological development and the European sovereignty. And one point that we want to stress is that we are aiming at having what we call challenge-driven strategic access, so that there are some specific topics which are related to the challenge of the society we are facing, that for which we want to have dedicated beam time in the different facilities according to the needs. And this access is meant especially also for industry. And you can find in one of the village, there is a booth of LEAPs. I invite you to go there, because you can find a copy of this strategy, and there is a poster, and you can there also ask questions to the people of LEAPs who are in the booth. And with this, I end. Thanks.
Yeah, thank you very much, Katharina, for sharing your deep insight in regard to the possible use of synchrotrons, making the link also with the circular economy approach presented by Fabrice. And I like very much your plea to collaborate. And events like today, of course, are meant to foster collaboration, to bringing the various competencies and capacities together to make the best use here in Europe, serving Europe and the world. And with this, I'm happy to now go over to our third intervention from Weiko, who will add more examples in regard to the importance and challenges of critical raw materials. Thank you very much for being with us, Weiko. The floor is yours.
Thank you. Use the PDF. PDF? Yeah. Okay. Thank you for the introduction, and good morning, everyone. So I will add some extra examples what we are developing to my research group and also other research groups in the Tallinn University of Technology. And I will also start with where we are. So I'm coming from this campus. So it's also, you can see it's really green here, our campus. I know that Grenoble is the green city of the EU this year, and that Tallinn is next year the green city of the year. So welcome to Tallinn next year to enjoy this kind of the green environment what we have in Tallinn and also surroundings of our campus. But like in the morning session, there also was that which kind of like stakeholder group is missing to engaging. And all the panelists like mentioned like the citizens. So it's like the wider society is like missing with the, like in the discussion how we can turn the linear business model to circular business model. So I would say that academia has the role here to educate also like the wider society here. And with this, or we are looking closer the houses what we have, where we are living in our everyday. So we can see that we are using the different types of raw materials in everyday life. And we should also distribute this information for the local people in every nation, that they understand that we need the raw materials to having the living standards that we have right now, but some materials are critical, so we have to mine or recycle them in that place where they are, and engage the local people to those developments what is planned. It's like the mining site opening or building the recycling plant. It has to be engage the local people. And this is just to illustrate that everyone we have these kind of smartphones in our pocket. And then there's also my favorite question is that how often you change that? Because everywhere each producer will give the upgrade of the model, and everyone wants to be the newest in the pocket. And what you do with the old version? You put it on the table at your home, and if we are living this kind of houses, what is on the photo, so you are collecting the smartphones. Your neighbor is collecting the smartphones. So you all collecting the critical raw materials at your home. And you should recycle the old phones, because all the data what you have here is in the clouds. You just have to synchronize it with your new phone. But also maybe this model is not so old, but maybe the other person can also reuse it. So this is the reusing the equipment is also important. And we have to also deliver the understanding of this kind of to the local communities. Because we have been used the raw materials already centuries. And each year we are using more and more different types of materials. And this is just to illustrate that this is the old model. When we extract the materials, we build the equipment, we distribute to the users, then we use it, and then it's just disposed to the landfill. But nowadays the technology is developed, and of course from the landfills we can also recover some materials, but we can use it as a byproduct. But to achieve the ambitious plans, what we have the Green Deal and other activities in the EU level, then we need to change our mindset. We see that already in the industry and in academia, this kind of behavior, but we have to move this behavior also to the society, that every citizen in every country can understand and using the equipment as much as possible, and then recycling that. And when we are talking about the mining the raw materials or recycling the minerals, then it's all about the crushing, separating, leaching the minerals out. It doesn't actually big difference is the virgin materials or secondary raw materials. We have to need to separate them. And we have to do it that in also the smart way, that we should using the all those technologies which is out there, the technologies like machine learning, AI, to integrate to the system. And of course, using the renewable energy to run those machinery behind those processes. And I will shortly explain 3 examples what our research groups in Tallinn University of Technology are working. And some of those activities is also mentioned before in this in the conference, and I will starting from that we have very good collaboration with the Ragn-Sells group, and they are using the waste material. It's the burned oil shale, ash, and they have developed the technology how to collect the calcium carbonate out of the ash. And then they are turning this calcium carbonate as a carbon negative product during that process, what they have developed together with our researchers. Then the second example is also from the Estonian oil shale industry. But here is the mining waste. So because of the oil shale seam consists of oil shale layers and limestone layers, and the oil shale goes to the production plant, and the limestone remains as a heaps, as a waste rock. But it's the pure limestone, so we can also get out the calcium carbonate out that. We can also separate the smallest particles of the oil shale, which is actually a kerogen mineral, and it's also important in chemistry. And the larger particles we can also use as aggregates to building the roads, to building the infrastructure. And similar mining waste sites are many in Europe. So we should research how we can use the old waste heaps of the mining sites. And then the third one is how we can close the loop with the building materials. So we have built houses centuries. The houses is getting old. We have to demolish them, but then just not putting the waste to the landfill. We should think what kind of minerals we can get out of there, and then plan this kind of processing plant for that. And because the different construction materials is being used in different countries, so there can be also different raw materials can bring out from the demolition or construction waste. And using that waste as for example, in stormwater filters, and after that cleaning the filters and using the new infrastructure also. So this is the closing loop of the building materials. And I would say the main challenge is that how we can build up or using the available technology in our service. And of course, the one possible way can be the digital twin. So we are making all the measurements in digital way before we are really starting the building the exact plant. And when we are building the digital twin, then we can use the different industrial virtual reality, augmented reality scenarios, using the machine learning opportunities, AI opportunities, and really plan in long term those processes. And then reflecting back to the society, that they understand that this technology is there, and it's not this kind of the dirty work, but the construction people are doing or the mining people are doing in the site, but it's running by the technology. And like I mentioned, that academia is about education and educating the next level CEOs and other specialists. Then together with other colleagues from other universities, we have built this kind of fully online course, and it's open for everyone, every student or management level people who want to educate using the credit points for their certificate, they can take this course from Tallinn University of Technology. Here is also the link of the course and the program lead email address, so you can approach to her. And that's all from my side for right now. Thank you.
Yeah, thank you very much, Veiko. I really explicitly like your clear pointing out of the role of digitization, that this is another opportunity for mastering these challenges, and also the reminder that the education perspective should not be forgotten. I think we all remember very well that in the morning we also talked about how to get the acceptance from the broad society, and therefore we really find a way to communicate in a proper way to everyone. And multiplying with the education system, I think, is a smart way. So now, therefore, it's now my pleasure to introduce our fourth speaker, Frederick, who will, as I already said, give us some deep dive analysis in one specific field of the critical raw materials, which is also very familiar to us, which are the magnets. So very pleased to have you with us, and the floor is yours, Frederick.
Thank you. Good morning, everyone. I am Frédéric Caroncotte. I will first talk a little bit about Carester. Carester is a company I have created in February 2019, then a little bit more than 3 years ago. We were 6 when we started. We work on 2 different topics. The first one is to support mining companies who have rare earth projects, but they don't know. They are good miners, but they don't know rare earth, and then we help them to optimize their chemical process to make rare earth. This is the first activity. Second activity is we have a project to recycle rare earth from end of life. We were 6 3 years ago. We are now 26, and we continue to grow. And then I will talk about rare earth. What I missed to say is we work on rare earth, and rare earth. Everything outside of rare earth, we don't know anything. Then, what about rare earth? First, a lot of people are talking about that. Rare earth somewhere. We saw, for example, in the first slide of Fabrice this morning that rare earth was on the top of the criticity of the critical raw material. When rare earths are critical. They are critical, why? Because they are key for energy transition. When we talk about energy transition, we always very often talk about electrification. Then we very often talk about batteries. Batteries is a point, is necessary to store the energy. But with only battery, the car will not move. To have a car which will move, you need a motor. And more than 90% of the motors which are used, of the electric motors, are equipped with magnets, with rare earth magnets. Why rare earth magnets? Is because the rare earth magnets are the most powerful commercial magnet which exist. Which means that if you need a magnet for your motor, and if you need to be light, or if you need to be small, you will use rare earth magnet. Then the first message I want to deliver is rare earths are key for electrical mobility, but not for batteries, for motors. Because very often I have message of people who say, oh, rare earth in battery, yes, it's very important. No, in battery you have lithium, cobalt, nickel, copper, but no rare earth. But rare earths are associated with the motors. And just an example, 100% of the electric scooters that you have in the road are equipped with magnets. From 100 grams to 300 grams of rare earth magnet in each electric scooter. All of them. Same for EVs. If you talk about traction motors for EVs, 95% are equipped with magnets, rare earth magnets, sorry. Same for wind turbine. Wind turbine are not same. Wind turbine, all wind turbine do not have magnets. Some are with gear, some are with direct drive. Magnets is very often in direct drive, and magnets is used more often for the offshore wind turbines because as you do not have gear, you have less maintenance. Then you have magnets. I talked about 100 grams in an e-scooter. A little bit less than 1 kg in electric drive in electric vehicle. More, it can be more, it's between 500 kg and 4 tons of magnet in a wind turbine. The new one for offshore is 4 tons per wind turbine. Then you have permanent magnet in a lot of applications which are key for the electrification of our world. Second is, okay, magnet rare earth. But rare earth is a metal, is a group of 15 metals. And all the rare earth are not critical. Why? You have 15 metals. Each time you dig into the earth to have rare earth, you have 15. The one who tells you, I have only 4, don't trust him. Don't trust him. Always 15. And always radioactivity. Always. In all deposits. After that, in application, you have the 15. In application, it makes sense only if they are separated one from each other. A bunch of rare earth has no value. It has value, sorry, but it cannot be used like it is in application. You need to separate it. You need to separate it, and then you need to have them pure. This is the reason why we talk about rare earth. It's not because it is rare. It is because it is rare to have it at pure level. You can have the 15 easily, but to purify is not so easy. Now, out of the 15, which ones are really critical? The ones which are critical are the ones which are linked with the magnet. The 4 ones which are in light blue, neodymium, praseodymium, dysprosium, terbium. They represent these 4 more than 90% of the value of the 15 rare earth. But they represent much less than 20% of the volume. It means that here, the criticality is on these 4 rare earth. For these 4 rare earth, which allow to make magnet, the demand in 10 years will minimum double. Minimum double. This is what you see in the right-hand side. This is the most conservative figure I have found. I can show you also much more optimistic one, but the minimum is multiplied by 2. Today, 60% of the mines are coming from China. Like Fabrice said, it's good to have the mine outside of China, but be careful. You need also to have the processing outside of China. And here, what you see here in the bottom is for mining 60% in China. But when you go to the supply chain, it is going from 60 to 94%. It means that you have a lot of mines which today send their ore to China for processing, which means that you go from 60 to 94. And if I am more accurate, I should say that in the rare earth group, you have here on the top, you have neodymium, praseodymium. Here you have some outside of China. But if I make this slide just for dysprosium, terbium, which are heavy rare earth, here you don't have 60, 87, 91, 94. You have 100, 100, 100, 100. It means that today, every motor which is in an electric car is containing dysprosium. It is coming from China today. Today. For the heavy rare earth, dysprosium, terbium, 100% is coming from China. Then we need to do something, because we cannot say it will double. We like the mobility, we like the electrification, but we depend only and more on China. To do, you have countries, you have regions which are reacting. And when they react, it's not small thing. I just put some example, which the oldest one is coming from 3rd of April 2022. It's not 10 years ago, it's 3 months ago. Australia has announced that they will put up to 2 billion Australian dollar to a company which is called Iluka in order to make light and heavy rare earth from their own mine. In Australia, they have a mine. They have a lot of mines. Then they put money to say, we need to mine more and to process more. The US are also reacting by putting money. Here is just what they have put in the last month, but they have put much, much more in the past to MP Materials. MP Materials is the former Molycorp, for the one who knows, is the biggest mine historically used in the world. It is in California. It has restarted about 5 years ago. Today, MP Materials is extracting thousands of tons of rare earth, sending directly to China. They have projects to make all the chain in the US. The last announcement, a few days ago, Lynas, Australian company, has been awarded by $120 million just to put a refining unit in the US. The US, the DoD, pay 100% of the capex. 100% of the capex, not 10, not 50, 100%. And they say, okay, we want that, boom. Then in Europe, we need to react. If we don't react, we will depend on all of them. In Europe, we don't have big mine. We don't have big rare earth mine. We will not have in the near future. But we are big consumer of electrification. Then we have a good mine, which is the urban mining. The urban mine. What is the best ore to make a magnet? A magnet itself. The magnet itself is containing the 4 rare earths that we need, where an ore is containing 15. Then you have only the 4 that you need. You have plenty everywhere. Now, need to collect, to make the job. Then, people will tell you, told me in 2019 when I started this project, you are okay, but you are a dreamer. Because electrification, electrical cars, is not before 2040. I say 2 things. The first is, when I see specialists talking about cars, nobody agrees with his neighbor. But everybody agrees on one thing, is when they update their numbers, they increase their numbers. This means that if it's 2040, it will come earlier. Second is, it is true that electric cars duration is 19 years, but what about an e-scooter? E-scooter is several months, no more, today. Then you have urban mine today, every day, which you have magnets, which every day are going to scrappers, and they are lost with the iron and so on and so on. This is small, start very small. But there is one thing which is accelerating the path for me, is we need more and more magnets. Today, you start to have projects to make magnet units in Europe. When you make a magnet unit, just the end unit, you have between 10% and 20% of scraps. They call that swarf. When you make a magnet, you need to cut the magnet. When you cut the magnet, you have loss of production. Today is minimum 10%. It can go to 20, even more. Today, you have German producer of magnets. They send their products to China. And we have it. We can take it. We can keep it. And here is not one magnet in 100-gram magnet. It is 10% of the production. Then you have also new project coming. And the idea is to say, we need to grab this, to keep it in Europe. Second, you have all car makers. You have all people who are working for car makers who are making the motors and so on. They assemble the magnet. When you assemble a magnet, you have also loss of production. 1%, something like that. Today, this loss of production is either totally lost or sent to China. Then what we say is, in Europe, we can make a unit, we can make processing not based purely on mining, but based on recycling. And recycling is not for dreamer in 2020. It can start now. It can start now. It's not, for us, we say it's not too early to develop recycling. But with recycling, if I say 10% of the production of magnets, if I say 1 or 2% of the assembly companies, if I say end of life coming step by step, I will never multiply by 2 the offer. For that, what we say is we need to combine recycling and mining. We cannot say we should not oppose recycling with mining. For this critical material, we need both. And for us, we think that Europe can play a key role in recycling and mining. And this is a project that we are making. This project to start a unit to recycle 1,000 tons of end-of-life magnet plus 1,000 tons of swarf scraps from production. We have started this project in 2019. We have received a subsidy from French government within the recovery plan. We have received 15 million euros subsidy to make this demonstration. We will make this demonstration in south of France. We have started the engineering. Decision of investment end of this year for a start up in 2024. Startup in 2024. With that, we will be able to make some rare earth, 600 tons of rare earth, where we will guarantee that it is recycled product, it is recycled molecule, it is not a mass balance, it is a real recycled molecule. We will have also small quantity of this heavy rare earth, the dysprosium terbium that you see in the bottom. I said before, today 100% is coming from China. Here we will have a small quantity. And it is here where we want to combine mining with recycling. Instead of making a small separation unit of dysprosium terbium, we'll make a bigger one. And we will tell to mining companies that we support for optimizing their process within the first part of our activity, we'll tell them, instead of making the separation of light rare earth in your plant and sending the heavy rare earth to China, send to us, we will treat for you, and you will have back this dysprosium and this terbium. And the target behind that is to attract metal alloy producer and magnet producer. Then at the end, we will have to recycle all of them, and we will close the loop. This is a project that we are developing. We want with that, it will be the first demonstration unit in the world able to produce such quantity based on recycling. Now, I like to finish like that for French guys, is when we talk about future, it's us, Antoine de Saint-Exupéry, not me, who said, as far as you talk about future, it's not about forecasting it, but making it. And this is what I try to say to within our company. And last word is, I have almost 4 children, and my 5th children should in the next day, should come in the next days, when we should remember that we act for our children. Thank you.
Yeah, thank you very much for this very empathic speech about the role of the rare earth and the situation we are facing in the EU. So now I'd like to ask all the speakers to join me on stage so that we can open the panel discussion. So the colleagues will help us with a few chairs. And maybe while we are then preparing this new setup, I'd like to remind you that you are very welcome to interact with us via Slido. Please put your comments and your questions using the well-known Slido system. And my first question is addressing you panelists again. And we've seen with Frederick this strong plea for fighting the dependency towards China. And as this is the critical raw materials session, I'd like a more explicit statement from you as the experts in the field. How do you see this approach we have with the critical raw material definition? Is this a good, a valid approach? Can we be happy with this? Do you see that there are more activities needed? You may give some insight what additional activities may be needed.
If I can start, I would say for me there are two things which are the core of everything. The first one is regulation. Regulation is to say if we say that materials are critical, if when we have in Europe, it should stay in Europe. We should work for that. If it is critical, if we say that we need it, we pay already one time when it comes to Europe, because if you pay to a mining company, which can be outside of Europe, we should make everything to keep it in Europe. The second thing is money is essential. Today we fight against regions who are putting a lot of money. And tomorrow you will have to compete against them. Then money is essential. And I will finish by the last point to say we need to be quick, because there will not be room for everybody. We need to be quick. If we are not quick, others will react before us, and at the end we will be dependent not only on one country and several others, but we need to be quick.
I want to build a lot on that. Actually, he has said most of what I wanted to say. But if I take the analogy of thermodynamics and kinetics, so on thermodynamics, I think we're pretty good because we are developing the best technologies to recover as much as possible. On kinetics, Europe is usually not the fastest region in the world to do stuff. I mean, we are very good at saying what we should do, but we are less good at doing it. And there, one point that I find very important is permitting. You can have all the money in the world, you can have a site, you can have the people, and then if you have an administration that makes your life miserable because they take years and years and years to permit something, this is not going to work. So we have to be as fast as possible. And of course, we should not work against the environmental laws. That's not the purpose. But instead of having 5 people in the ministry that is doing the permitting, put 15. And just make it fast. And there, I think that this is really more a member state or regional element than European Commission having to be blamed in a way. They are putting the framework in place, but the member states and the regions are usually not following as fast as needed. And some countries are of course better than others, but in general, if we compare with China or, I don't know, of United States or maybe some South American countries, we are really slow.
Well,
Just speak.
I think I agree with what was said. No, I agree with what has been said, of course, and I think we need more a stronger Europe. Because, of course, what is the difference between Europe, China, and US? US is one administration. China is one administration. And they, as you say, they put the money in. Europe is a collection of different administrations. We have the European Parliament, but is the strong power is in the member states. And the challenge for the future is so severe that we need to have more Europe, a stronger Europe. And this is something that is politics more than science or economics. But I think this is the only way that Europe can compete with the others is putting together all the forces, and for that we need something that join the administration of the different member states.
Okay, I think these were very clear statements. Hopefully they will be listened as thoroughly as needed. Let's go to the other perspective. How full is the pipeline of ideas, so to speak? We've also the research experts with us. So I'd like to throw the question more in the direction, what do you think, are we full of ideas in regard to identify new promising solutions to reduce the dependency for us as Europeans on critical raw materials from outside sources and are more and more sovereign in this respect? And if I may be more precise, we've already touched upon this, what kind of research do you think is good in place or maybe needs more attention, the blue sky research or more the applied research? What are your views, please?
Yeah, I will start with that there are always good ideas. And in the European level, we have also like the build the structures. For example, the EIT, which is like the Technology and Innovation Institute in Budapest. They have like the 8 different networks for each industry, and it's also like the EIT raw materials there, and there are the structures where they can push those ideas and also fund the ideas in the early stage. And for a very good example is the jump starter, where there are like different fields where the students already can give the ideas how they want to change the future, the technology, and then there are the experts from the field and evaluating the ideas. And I would say that the startup scene in Europe is growing and good actually also in Estonia. And in that sense, we can also like be the example for the other countries. Yeah.
Yeah, please.
It's working. I also wanted not to stress that recycling is the solution to everything in the presentation, but of course mining. And in mining, if I would look at the company of Umicore 15 years ago, I would always be surrounded by colleagues who had a mining engineering background. They were getting older and then they retired. And now I'm surrounded by people who actually, most of them, they have no mining engineering background. And if we want to reopen mine in Europe, we are actually going to suffer because we're not having access to the talent. If I would ask my colleagues in China, do you know many mining engineers? They would all say, yes, we know many. So there is also a signal to be sent to the people who are now going through high school and then to university that, for example, mining is not a dirty word, and it's good to study mining engineering or metallurgical engineering. These people, they are very rare, so we end up importing talent also from actually China sometimes, not just the materials, but we also import the brains. And so that's also one message, is that we have to educate the future workforce.
I think that's a very important point from Rossi's perspective. I couldn't agree more with the metallurgical perspective. And yes, this attitude creation in public has a huge influence. Also in regard to the choices of the young generation, and there we all need to work together, I believe, to provide a proper set of information so that they can make informed judgment and not just something like Twitter-based judgments. I think that's the challenge for us. Yeah, and we can also see that through Slido we are asked to maybe dig a little bit more into the question of this electromobility and the situation of the batteries. So how do you see if I go to the lower one, how do you see the practical challenges in the recycling process of EV batteries? So this seems to be quite a complex process and needs still a couple of new innovations.
Well, actually, the presentation I gave listed all the challenges, whether you are recycling a windmill or if you're recycling an EV, is pretty much the same. So You have to collect, you have to move things around, and if it's a EV battery, it's actually making our life quite difficult to get the battery from where it is discarded to where it is recycled. Then you need to recycle it with the best technology. And then, of course, you have to fulfill the legislation. And for companies like Umicore, which are doing recycling pretty well, sometimes we believe the regulations are actually not strong enough, because a regulation which is not strong is also encouraging recyclers to develop in Europe, which are actually not doing recycling as it should be doing, or actually do not recycle because they stop in the middle of the process and then they leave their problems to someone else. So I think one of the challenges is actually maybe not so technological, but it's to have the right legislation in place to make sure we do recycling the best way, because if the regulation does not push us to make it the right way, we're also going to end up with reputation issues, and recycling is going to be said by people, yeah, it's a dirty business, which is not a dirty business. It's dirty if you want to make it dirty. So there the challenges are not only technical. I think technically it's pretty okay. I mean, we have to continue doing research. We have to reduce the cost of recycling, so we have to make sure that we have processes which are at higher scale, and the bigger the pen in which you do metallurgy, the more challenges you may have. We have also to make sure we have processes that are able to accommodate batteries of different compositions, for example, not just one composition. And actually, maybe I want to finish on that. One of the biggest challenges with recycling is that recycling is not only when you put something in a smelter, it is also the dismantling. And dismantling EV cars, if they're all different from a different brand with a different battery, is going to be a hell of a job if it's not automatized and safe. So there's a lot of challenges on the robotization, automation part. And artificial intelligence, as you said, can help quite a lot.
Yeah, Frederick, please.
Yeah. Regarding batteries, I will not comment a lot because, as I said, there is no rare earth in batteries. The only thing I should say is, when I see the number of people who are working on batteries in that world, I am convinced that they will find solution, because you do not see any company who is not working on batteries today, almost. Regarding the rare earth metals, the comment today, rare earth metals are allowing to make the most efficient motors for electric vehicles, 95%, because they are the most efficient. But you have alternative technology. You have the Renault Zoe today is a car which is not using rare earth at all. When I say that, it is rare earth allows to make the most efficient motors. If it is too rare, if the price are too high, technology will switch. And for me, it's not a matter of stopping electricity. No, it's just to say, and this is what I say to all the mining companies and to all the chain, if you think that the price will skyrocket, you make a mistake, because it will skyrocket, but then switch to other technology. I was in rare earth in 2011. I was in charge of a plant. In 2011, there was a big crisis on rare earth. The price for cerium, for example, used in auto catalyst, moved from $2 to $100 per kg. The price of terbium used in the lamps moved from 600 euro per kg to more than 3,000 euro. For cars, no possibility to switch, then stay with the same technology. For lamps, what has been the solution? Full speed to LED. If you check the fluorescent lamps that we all had in our house, in a few months, it has disappeared. It has disappeared, and we were in the recycling of that lamp. It has disappeared not because it was planned, it has disappeared because of the price. And this is, for me, the point is not to say we should move back to thermic. No. It's say today is the most efficient, but if it's too expensive, there will be switch.
Okay, and maybe regarding the recycling, Fredrik, to my information, the recycling of this rare earth is also special because smelting is not an option. Can you elaborate a little bit on this as well?
You don't. You think that I will give you my secret? No, not at all. No. Yes, it is special. You are absolutely right that it is special. It is a mix between what we develop is a mix between pyrometallurgy and hydrometallurgy. The big target is in a magnet, what do you have? You have iron, more than 60%, boron, less than 10%, and rare earth, about 30%. Today, there are people who say, okay, I put everything in acid, I dissolve everything, and then I try to... This is not ecological, because you spend a lot of money, a lot of reagents. And what we try to do, is just to select just the rare earth. We also want to recycle boron, because boron will go with iron, and then we waste. What we say, no, for us, we will recycle also boron. For that, yes, it is special technologies. We are developing it. We are patenting it. I hope that by end of November, we will have 8 patents related to all of that. It is special, but it is not impossible. And when you combine know-how about metallurgy, know-how about rare earth, know-how about mining, at the end, you can find something good. And for me, the most important, and what we are trying to develop, is to work on proven technologies, not to try to invent things which will work industrially in 20 years. This is it. But it's not impossible, and we can have a reference recycling unit in Europe in 2024. We can. We just have to do it.
Yeah, so I could see also the other panelists nodding, which made me make some exclamation marks behind the already noted down statement that we should work on accelerating regulation improvements, relaxations, as well as permitting relaxations, because we are not talking about some magic unknown processes. We are talking about very concrete solutions which we like to implement in order to improve the situation for Europe in regard to the critical raw materials. Yeah, so maybe we can come back to this collaboration perspective, which was so nicely presented also by Katharina, where she showed that from the scientific perspective they created this alliance to provide a good offer to all the ones thinking new solutions. What is your view? Do we have enough capacity? Is this well used? Is something additional needed? What is your view on this?
Of course, everything can be improved. There is already a strong interaction between public and private, but it should go. It should develop more. And I think also here having European projects where this public-private collaboration is made more easy also from the point of view of regulation, as we were saying, and with more funds put in specific topics, like the ones we are talking today here, will surely help. I mean, the instruments are there. Our instruments, when they started, were meant mainly for what today was called like blue sky research, instruments for advances in the knowledge. For increasing the knowledge of in the different fields. But we are more and more going towards applications. We need both of them, because without this blue sky research, you will not go towards new ideas of application. So we need that, and we need to strengthen the a platform where this collaboration can be better developed. Also here, talking about LEAPS, not only LEAPS, but also other analytical facilities which are now joining under ARIE, Analytical Research Infrastructure of Europe, where you have also neutrons, lasers, high-field magnets, and so on. This platform of different European research infrastructures put together, working together, and giving service to the community where the academy and the industry develop together solutions for our challenge is something that we aim at, and this is what we are talking also with the European Commission to help in this direction. Because it's clear that if you go in the different nations, there are already programs, but putting together the programs of all the different member states is the way to the real success.
Yeah.
Yeah, on the slide of Taltech, there was like a curve on the amount of metals that was more and more. We don't do this because we want to put more metals, but we do it because the applications become much more complicated. And so there's a reason why some metals exist. It's because they are useful. So the metals are more and more combined into very complex products. And what we see is that the cost of developing materials is actually skyrocketing. The time to develop materials is becoming longer and longer if we do use the same techniques. So we need to have new techniques to develop materials, which is what we have now highlighted in the manifesto, for example, and the roadmap. And many of these techniques, they are quite expensive investments as well. And so we have not everything under the same roof of the company. We need to be able to rely on partners which are external. Ideally, as has been said, in a form of league, because then you know where you can go and you know what is available. And I think it's also very important if you want to develop the startups and the companies of the future, companies that would not exist today, but would need to exist in the future. They need to be able to access these infrastructures.
Yeah. And maybe we can conclude with a question we can read on Slido. So I will read it for you. So, and everyone may comment with a brief statement. So the question here by Slido is, the trend we can see going to this renewable energy sourcing with hydrogen, fuel cells, and so forth, the photovoltaic. What does it have? What impact does it have in regard to our raw material dependency situation? Will it help us to become more independent, or will it be more neutral, or will it even worsen the situation? What is your view on that? Let's start the other way around, Frederick first.
I would say it's to go from an oil era to a metal era. Now you have different type of metals. You have one type of oil, and then to go from oil dependency to more metal dependency. You wanted me to be short?
Yes.
I would say, I would not use the word reduce, I would say may modify our dependency. So we're going to depend on many more metals coming from many more different countries. We will still be dependent because we have not such a good geology anywhere in Europe, and we can reduce this by recycling, but we will always be dependent on other countries. But they will be different.
From your answers that we will increase some flexibility, which can be perceived as a positive move, because flexibility is also helping to allow finding other solutions.
Absolutely.
Okay. So thank you very much also for the audience. So maybe give a nice round of applause to the panelists. Thank you very much, and please enjoy the lunch, and the session is closed. Thank you. Yeah. I enjoyed it too. It was